to the guest lecture on a particular topic in GPU programming, in particular techniques in graph algorithms on GPUs, which will be delivered by Rajesh Pandian. He is a PhD student in the department working with Professor Narayan Swami and me. His interest has been in the context of graph algorithms, so he's at the intersection of theory and practice. And he did his master's at IITM itself and then continued as a PhD student. He has been working on uh, making approximation algorithms for hard problems efficient on GPUs. And in particular, he has worked on Steiner tree problem, which is a generalization of the minimum spanning tree problem. And in general, whatever some of the basics of his research are going to be quite useful in the context of understanding some application of on GPUs. And therefore, I thought that this is going to be a useful aspect for us to learn from Rajesh. And I'm thankful to Rajesh for agreeing to give this talk. Over to you, Rajesh.
Thank you, Rupesh. Am I audible? I hope I'm audible.
Yeah, you are audible to me.
Yeah. Okay. I hope I'm audible to everyone as well. Okay, let me start. Uh, so I'm Rajesh. I'm working with Professor Rupesh and Narayan Swami. Yeah, I'm a PhD scholar in the department. So yeah, let's get started. So the topic is techniques in graph algorithms on GPU. So whatever I'm going to talk in the next few next 15 minutes is like whatever I have learned from both the profs and from the papers I have learned through. So I'm going to condense everything that I know with respect to related to GPU, and I'm going to distill in such a way that it can be taught as a 15-minute lecture. So, yeah. Okay, so these are the outline of the talk. First, I'll motivate why we need GPUs for computation. Next, I'll touch upon the graph properties and the graph representation that are helpful for helpful on GPUs, and these are the approaches, or we can call it as techniques, or we can call it as optimization. So, there are like a list of some 5 to 6 optimization techniques, like which can be combined one with the other, and we can improve the performance of any existing graph algorithm as such. So yeah, so let's get started. So why do we need GPUs for graph processing? So in the beginning, GPUs were only used for only graphics processing, which making the pixel colored, or pixel a little sharper, or a little shader, and so on. And when the programmable shaders, which made graphics and animations and graphics softwares, so which became they are called as like programmable shaders. Like when the shaders became programmable, then some people thought that why don't we use GPUs for general purpose computing? So then GPUs became a GPU. Now the context of GPUs is not well pronounced, but yeah, GPU means GPU. It became like that. So yeah, so initially CPUs were designed for like serial tasks, whereas GPUs and all these processing units, which are called as cores, are designed specifically for the arithmetic operations. So yeah, so not just that, like it has a extremely huge computation power. For example, like this supercomputer, which is made up of 64 Sandy Bridge CPUs, which can take some molecular dynamic simulation, which runs for like days, can be done with a single Tesla K40 GPU within a few hours. So like a small GPU attached to our PC can perform computation power equal to the I mean, more or less equal to the supercomputer back then, like 10 years ago. So not just that, like we the cost of the GPUs and maintenance cost and everything is comparatively lesser when compared with the supercomputers, and it is more energy efficient. For example, to get a exaflop, exa meaning 10 to the power 18 floating point operation using a CPU only supercomputer, the energy required is equal to the power that is needed to for two large districts in US, for a couple of days. So yeah, so this energy that is spent on CPU is very large, whereas GPUs consume comparatively lesser power and achieve a faster computation power. So these were the main motivation, and graphs are everywhere, like graphs starting from road network, social network, biological network, wireless networks, like graphs are everywhere, and such graphs are very extremely large, and like we expect a faster computation on those graphs. Like for example, like if you want to know a particular from the scan reports of whether there is a brain tumor, like or and so on, like we cannot make the computation run for like years or like months, right? Like we need results to get to the patient immediately, something like that. So we cannot run a weather forecasting or weather predictor to run for like for example, we need to predict the tomorrow's weather, then it should complete well within today, right? Like we cannot run that computation for days. So GPUs are helpful in accelerating whatever computation we have. And yeah, so these are some of the basic graph properties that we have learned, and like more or less these real graphs will map to some of these properties. So the graphs may be directed, undirected, weighted, unweighted, and like connected or disconnected. So like uh, yeah, so the standard graph theoretic notation, we use like a small n to denote the size of the vertices, and the size m to denote the size of the edges, right? So yeah, so vertex IDs are generally we map the vertex IDs on GPUs to 0 to n minus 1, which is the ideal case. But in general, real world graphs will not have such vertex ID. So it might be arbitrary, or it might be one off uh, away. So we have to remap to 0 to n minus 1 so that our processing is faster. Yeah. Okay, so these are the basic graph representation that we have learned in learned for serial CPU computation, which are this adjacency matrix and adjacency list, and both are very good, or very well, I should say, well explored in CPU setting, whereas the other two, which is called as edge list format, or coordinate format, and compressed sparse row format. So these are the two representation which are well suited for GPU. We'll get to it why they are better. Yeah, first up, yeah, let me take a small toy example to demonstrate this. Like let's take adjacency matrix. So what is an adjacency matrix? Like it is a n cross n matrix, so where n is the number of nodes, and each index denotes whether a particular vertex is incident on another particular vertex. Here we have taken an undirected graph, so the matrix is symmetrical. So if it was a weighted graph, then we would have weights instead of the ones here. So as we could see, there are a lot of zeros in the adjacency matrix, which we do not want it. So the next representation is like just throw out all the zeros. Let's store only the essential information. So that is the adjacency list, like for each of the particular node, and we store the corresponding I'm sorry. Just a minute. I just switched screen. Sorry for that. Okay. Okay. So yeah. Sorry, I got stuck. Okay. So this is basically throwing out all the zeros and combining all these non-zero items, non-zero indices collected one after the other. And this is adjacency list. And what is edge list format? Edge list format is like it captures each of the edge in two m-sized array here. So here. Yeah, so I should say it like 2m sized array, but yeah, so here basically if you look at it, like there are repetitions, right? Like this is the edge list representation, but this is not a very good representation, I should say. Like we can store it more in a compact fashion. So there are this zero getting repeated like the degree many times, right? Like so this can be actually compressed. So this is yeah, this is what we call as compressed sparse row representation, wherein each index here represents the node here, and each value in that particular index stores the first uh, neighbor. I mean, stores the first neighbor in the CSR list. So this the first array is called as offset array, which stores the offset, and the second array is like a CSR list, which stores the neighbors, and the value in the offset corresponds to the starting point of the neighbor list, right? Yeah. So note that like the offset array will contain one additional entry to know that is the end. Like since we are numbering from 0, like 16 is the end of a particular list. So anything between for example, if we want to find the neighbors of 2, then basically all the values starting from index 2 and whatever values before 5. So these are the node IDs of the neighbors, right? Okay, so this representation is very helpful in GPUs, and it is used everywhere. Let's get to an approach which is called as operator formulation approach. This approach was invented by Pingali and et al. In a famous paper called the Tau of Parallelism in Algorithms. So they formulated a pattern in which they can fit all the algorithms into this formulation. So what is this formulation? This formulation will have some initialization for the graphs or whatever we are going to compute. Then there is a fixed point block or a do while block inside which we'll perform a particular operator on it. So the operation could be on the set of edges or the set of nodes or something else. So when do we stop? So there is a condition for us to stop. It varies from algorithm to algorithm. For example, if the algorithm is single source shortest path or SSSP, then if there is no other change in the distances, then we can actually stop our algorithm. So they have fit some 4 different algorithms into this pattern, and after which many researchers found out that this pattern is a very applicable pattern, and they brought in more graph algorithms into this pattern. And yeah, and the important thing is this operator is applied in parallel. So this is the whole benefit of this operator formulation approach. So yeah, like I said earlier, like SSP, the operator is like will propagate the distance from source to the neighbors, and similarly BFS propagates the level information from source to the remaining vertices. Okay. Okay, let's take an undirected graph to simplify the matters. Like we assume there is a unit weight on all the edges. This is so whatever I'm going to talk in the next few slides can be applied to weighted graphs as well, but uh, just to explain, just for the explanation purpose, and to keep it simple, we have unit weights on the graph, right? Okay, so for any BFS or SSSP, so we should start from a source, and let's say A node be our source, and let's compute the distances from the source, or if it is BFS, then it is the levels from the source. So in case of undirected unweighted graph, then both the BFS and SSP will give us the same result. The levels and the distance array are the same here. So yeah. Okay, so this animation will show us how the levels are computed. So it goes in a stepwise fashion. So it computes each level at a time. So, and when all the levels are computed, the algorithm is done, right? Yeah. So yeah, so let's visualize this. How does how to compute an SSSP, or yeah, let me take let me call this as SSSP, although it may not look like an SSSP because we are using an unit weight graphs, but still it like even if we have a weighted edge, this will still hold. Okay. Okay, so as a first step in the SSSP, what is the first step? We'll have to initialize the distance arrays. Yeah, we'll initialize the distance arrays to infinity using by launching n threads, and set the distance for source to 0. So this is the initialization step in a single source shortest path thing. So in addition to distances, we could as well calculate a parent array or a predecessor array, which I'm not explicitly mentioning here, but we could still do the same here, right? Okay. So the green vertex will represent an active vertex. So at the start, so since we have set the distance of source, which is A here, to 0, and we also mark the start node as active. So okay. So the approach we are going to take now is called as data driven, and it is yeah, so it is called as data driven. It is given in the paper called topology driven and versus data driven for irregular algorithms. So yeah, so in data driven approach, so we will launch that many threads only uh, okay, sorry, we'll launch only the number of nodes that are active, only that many threads will launch it with. So in here, this only the source vertex is active, so we'll launch it with one threads. And what does that thread do? It relaxes the neighbors. So in some way it pushes the distance information from itself to all the neighbors. Okay, so let's see. So once it has pushed, so the neighbors now becomes active vertices. So then now, like, we should be launching 3 threads, the number of active nodes, many threads for the next iteration. So this is what that the operator formulation, which I showed you a couple of slides ago. So in here the operator is relaxing the neighbors, and our condition for stopping is when there is no more active vertices, then we should stop computing or stop applying the operator, right? Okay, so yeah, so each thread will relax its neighbors, and it goes on. So for all the active nodes, the operator here, yeah, I went a slide ahead. So for all the nodes, the operator here is relax on its neighbors. So yeah. Okay. So at this iteration, like E and F are active, and they are pushing the data values to the neighbors, and it makes G, H, J to be active, and three threads are launched to update the neighbors of G, H, J, and it so happens to be that uh, uh, the, which is a common vertex, and their distance gets updated as 4, right? Okay, so what is next?
I have a question. Can I ask?
Yes, yes.
So this seems very ideal for uh, CPU kind of system, right? But for GPU, there could be huge amount of divergence due to this, right?
Right.
So
Yeah.
can you explain like why GPUs are preferred for this?
Yeah, we are actually getting into what you had asked. So this approach is it begins slowly, but when it is like when the iterations are in the middle, like it will have a lot of computation. So the next technique that we are going to see is well suited for GPUs. This is also a technique that is used in GPU. So yeah, I'll explain the topology driven approach, and maybe that will clear what you were asking. Okay. I okay. Okay, so before I get to topology driven, so this data driven approach, how it is implemented. So this is implemented using a work list approach. So work list is nothing but an array in which we put all the active vertices or active node IDs into that list. So whenever we mark a particular vertex or a particular neighbor as modified, then we'll push it into that work list, and we'll only launch work list many threads. And yeah, the important point here is, like, when updating the work list, we have to take care of synchronization, because multiple threads may try to insert a node, active node, into the work list. Yeah, so this is what data driven is. Now we are going to see what is a topology driven is. Okay, in topology driven, there is no specific active set. Every node is assumed to be active, so which means that, like, every node is active. So basically we launch n many threads, and each thread will relax its neighbors. So this yeah, this is one kind of approach, and what I have said earlier is other kind of approach. Both actually works well on different set of graphs, which yeah, which are which I'll not talk in this lecture, but this lecture is to give what are the techniques that are used in the uh, GPU setting, right? So this topology driven approach, yeah, like I said, like uh, n threads are launched and the computation is performed. Just like the previous data driven approach, here also, to initialize like the distance arrays are set to infinity except the source, which is set to 0. This can be done with n by launching n threads, right? Yeah. So yeah. Okay. So how does um, the topology driven approach works? As I said earlier, like every node is pushing the data, or the pushing the distance from itself to its neighbors. So imagine we can imagine this like a heartbeat or a ripple kind of effect at each vertex. So if we throw a stone inside a pond or something, the ripple happens, right? So just like that, this computation happens. So I'll show with an animation, but before that, this is a different perspective of what will happen. So there are n nodes, and we have n threads. Each thread is assigned to one particular node, and each thread performs a relax which is happening in parallel, but each one of the relax is for a particular thread happens in in sequential fashion, but overall the relax on its neighbors happens in parallel. Okay, so for a particular vertex, each of the neighbor relax happens one after the other. That is what I meant by sequential here. But yeah, so how long we should do this till there is no change is happening at a particular vertex? Then when there is no change, then we basically stop.
Rajesh, there is a question by Prasanna.
Yeah.
He asks, a node can have multiple parents. How is that handled while inserting in the workings?
Yeah, so a node can have multiple parents. Here, basically, we are actually pushing the data into the okay. Yeah, there will be duplicates. There will be duplicates like I mean, a particular node will be pushed multiple times. Then basically, we just have to remove the duplicates when launching the kernel. So that is a minor detail which will get into the implementation when we get. Yeah, we have to deal in the implementation. So I hope I have answered the question. Yes. Okay. Okay. Okay, so yeah, so this is how a topology driven push works. And why do we call this as push? As I have been repeating this word multiple times. So each vertex actually pushes the data from itself to the neighbors. So yeah, so the animation I'm going to show here is it is like a heartbeat algorithm. So like each of this push will happen in parallel, and note that like as you have said earlier, like when a particular node can have multiple parents, right? So this uh, yeah, so when updating the distance, we have to be little careful, like we have to use atomics to update the distance of the particular neighbor, otherwise uh, will not get the correct values. I'm purposely hiding here, like I'm not showing the update of parent here in push, because like we cannot directly update the parent array here. So but this code snippet that we are showing here, like this is the operator here, and you being the thread id, and or the current node current thread that is being operating on, and we being the all the neighbors of you. Basically we just compute the new cost from whatever we have computed for you plus that corresponding edge, whether that new cost, whether it is lesser than the old cost. If so, then we basically update the distance of v. So again, yeah, we have to use atomics here because there is a data race here, like otherwise we'll get into issues. So yeah. Okay. Yeah, so as I said earlier, like there is a problem with updating parent here, uh, right? So yeah, there is one other variant which we can do. So we have been pushing the data from a particular node to its neighbors, right? So alternative approach, what we could do is we could assume that the data comes from the neighbors, and which means that we are actually pulling the data from the neighbors. So we are iterating through the neighbors, but instead of pushing the distance from itself to its neighbors, we are actually pulling the data from the neighbors and updating ourselves. So this is called as pull approach. So yeah, so this use of pull will actually help in many cases, because here we can see that there is no atomics here, and updating the parent array is easy. So I have purposely not showed the update of parent array in the push version. So whereas pull approach for SSSP, we can update the parent very easily, because there is only one thread writing at a particular index, right? So there is yeah, the overhead of atomics is removed here, and parent update is also easy here, right? So yeah, so these are the changes, like uh, yeah, in order to make the a push approach into a pull approach, the high I have highlighted the changes here. So basically the adjacency list running of I mean, we run over the adjacency list or the neighbor vertices, right? That remains the same. And this particular, like previously it was d of u, and now it is like d of v. So that, yeah, that is a, like, with a minor change we will be able to get to a pull version, which is which slightly has a edge over the push implementation. And again, in here also, like, we are talking about topology driven pull. So like every node is assumed to be active, and thereby irrespective of whether a particular node is being updated or not, that particular thread will do a work of running over the neighbors and see if it can update update itself using the neighbors. Okay. Yeah, I will show you the animation for pull approach, which actually happens in parallel for each of the vertex. But since I cannot show the animation for all the vertices together, so I have animated in such a way that it is understandable. Yeah, so previously we had issues as is in updating a particular node, when there was a data race in updating a particular node when it has a common neighbor, right? So for example, B, C, D had a common neighbor E. So here yeah, here that is actually avoided, because this thread that is operating on E will only update itself. So there is that is why we do not need atomics here. And yeah. Okay. Yeah, irrespective of whether it is push based or pull based, a topology driven approach will run for a few iteration, and when the fixed point is reached, which means that when all the distances from the sources are updated, it will stop. I mean, there will be no more vertex updation happening, which means that we have reached a fixed point state, and that shows the end of the algorithm, right? Yeah, so yeah, so these so we have seen two approaches here till now. So data driven and topology driven. And topology driven launches n threads, whereas data driven launches an active set many threads for computation. Here we can actually combine both these techniques by using a simple bit mask array, which actually keeps track of only the modified nodes. So whenever the vertex is being modified, so like we have highlighted the change in the code for this. Like whenever there is a vertex is modified, we just have to mark that particular vertex as true, and this value, I mean this bit vector, will be used for um, used in the next iteration. So I have mentioned that earlier, like irrespective of whether there is work done at a particular node or not, a particular thread has to run over all the neighbors, right? So this flag actually helps us avoid that unnecessary task when there is no update on a particular node. So yeah, so this check is added at the top to for the SSSP kernel. Here, this kernel that I have mentioned is a push based kernel. So yeah, so by simply having a modified bit vector, we will be able to achieve a totally a different technique combining both the topology driven and data driven, and this approach works well on certain graphs, which individually topology driven or data driven would not have done a better job there. Right. So yeah, so we are moving on to a different.
Rajesh,
Yes.
there is a question from Prasanna. He says that so in this approach, I think he's asking about the topology driven.
Yeah.
We need number of threads equal to number of nodes which are yet to be updated at each iteration, which will be higher than the last approach. I think he's talking about the data driven as the last approach.
Uh, should I see? Can you repeat the question, Rupesh?
Yeah, so he's asking, will it be like the number of threads will be higher compared to the data driven approach?
Yeah, it will be higher. Like there are, I mean, there are totally n nodes, right? Like we at any point in time, like even if all the nodes are active in the data driven approach, we'll only launch n threads. Yeah, so yes, this data driven approach actually starts up slowly, and it with initially with possibly lesser number of threads, and the work done will be concentrated at the center of the iteration. So I have show I mean we have seen that do while loop iteration, right? So the large chunk of work will be done at the middle part of the iteration, whereas in topology driven approach most of the work will be done at the beginning of the iteration. So I do not know if I can write something on this. So basically data driven approach will look something like this. So assume that x-axis will be the work done, or the number of threads launched. So the chunk of work will be done at the middle portion of the iteration. So this will be data driven, and for similarly for topology driven, um, it is something of this sort. So it start more work will be done at the beginning, and eventually it will be tapering out. So I hope this clarifies. So yeah, data driven will launch. Short answer to that question is like data driven will launch lesser number of threads compared to the topology driven, but yeah, it will not exceed anyway n. Yeah, that's it.
Follow-up question by Prasanna is that will it change the number of iterations taken by data-driven versus topology-driven, or will they take the same number of iterations for fixed point?
Yeah, they will be different. Yeah, actually, so everything happens in parallel, right? Even a two different invocations, according to me, like if we take a very randomized weighted graph, like even a two different invocation of the same implementation of the topology driven approach will more or less take a, different number of iterations value. This is, yeah, this is what I could think of. because everything happens in parallel, right? Like even a small different order of execution in the thread will change the number of iterations. I don't know if it is right, but Rupesh can correct me if I'm wrong.
Yeah, so I think I'll just explain what you just said. So Rajesh is saying that even if you have the same implementation because of the way non-determinism exists in these parallel graph algorithms, the number of iterations can actually end up being a little different depending upon how threads are scheduled and how the values are getting computed, and therefore it can be different across data driven as well as topology driven. But Prasanna is currently not convinced that because it's the he's asking that in each iteration the same number of nodes will get the correct distance, right? So that is what he's probably claiming. So Rajesh, do you have any thoughts on that?
Oh, the claim is data driven and topology driven will have same number of iteration. Is it so?
Yeah, that is what Prasanna is arguing for.
Yeah, my answer is it will not have, but we have to check. Yeah, it will not have, but I don't have a proof as such. But yeah, this is my thought as of now.
Sure. So in case of this example of
Yeah.
let's say BFS, which was there on the slide, how does the data driven and topology driven happen across iterations?
Yeah. Okay. Okay. So yeah. So maybe the number of iteration is same for if it is an weighted unweighted graph, Rupesh.
Hmm.
uh, Unweighted undirected graph. But yeah, but my answer was generic. But yeah, I think I lost your question midway, so can you repeat your question?
Yeah. So in this case, for example, when you start with A and then settle the distances for BCD in data driven versus topology driven,
Yeah.
um, will it happen like in the same iteration, the same number of nodes will they will have their distances settled, or will it take different number of iterations in DD versus TD?
Okay, so your question, I'll repeat what you said. So you're asking at each iteration of topology driven and data driven, will the distances settled, the vertex for which distances settled, will it be same? Is that your question?
Right, right, right.
Yeah. Okay. Okay. So yeah. Yeah, I cannot think of it right now.
Okay, sure, no problem. I think we'll discuss this later.
Yeah. Sure.
Please go.
Okay. Okay, for some reason my slide is slow. Okay. Okay, so we are moving on to a different technique, which is called as unrolling, or which we call it as T delta optimization. So in general, graph algorithms are like memory bounds. There are lots of load store. So it is essential we do a lot of computation. I mean, we give more work per thread, like so. Yeah, so in both topology driven and data driven, like each thread will perform a delta amount of work. By delta I mean delta is the max degree of, in that particular graph. So like at most a thread can perform a max degree many work, right? So the idea here is, why don't we give more work? So how do we give more work? Like, so we what are we doing? So like we are updating neighbors, right? Like in case of push method. So why don't we stop? I mean, why do we have to stop there? Why don't we go and update neighbors of neighbors as well, which is like delta square amount of work, right? So we tried that approach for SSSP, but that was not performing better than the next approach that we are going to talk. So what is the next approach, which is repeat the work? So we are relaxing the neighbors, right? So that for loop that which is inside the kernel, which basically runs over the neighbors and relaxes the neighbors. So just repeat that for loop one more time, or say t many times, so which we call it as t delta. So when we tried that approach, which both push and pull, like, so it converges much faster than a normal single pull or a single push. So from our experiment on large test cases, we found out that, like, value 3 pull or 3 push to be an optimum value, so that which works well on most of the graphs. So this can be set to an arbitrary t value for a specific application as such, but in our case, the t value, which is when t equal to 3, we were getting a peak performance compared to a normal single pull or a single push SSP thing, right? Okay, so I'm late on the animation. Okay, sorry. Okay, so the next optimization that I'm going to talk is use of shared memory. So shared memory is the programmable cache kind of thing. So accessing from data from DRAM is a lot faster from shared memory than compared to DRAM. So why when we have to when we read multiple uh, sorry, when we read a particular data multiple times, for example, in case of t delta approach, we have to go over the neighbors adjacency list, right? So 3 times or t many times, right? So why don't we copy the neighbors into the shared memory, so that our rest of the t iterations will only have to read the adjacency list from the shared memory. So this is what we did. So yeah, so when we can move data to the shared memory when there are multiple reads. So yeah, so yeah. Okay, so but there is a limitation from the hardware, that there are only certain number of memory for the shared memory. So which limits us to something like uh, per thread we can only store 24 words for a particular thread. So when the degree of a particular node is lesser than say 25, then we could actually copy the entire adjacency list into the shared memory, and which will actually help the t delta optimization to run faster, and so in terms of running time, right? So yeah, so if the degree is little larger, I mean larger than 24, then basically we can store the first 24 neighbors alone into the shared memory, and rest of the neighbors can be read from the DRAM. So yeah, this is an approach which actually improved the which can improve the performance of our T delta optimization. Okay. Okay, very quickly, I'll complete in 5 minutes. So here I'll touch upon an algorithm which is for Steiner tree. So let's look at the first left-hand side of the figure, which is basically running the SSSP k times one after the other, and based on that computation of that SSSP, we create a graph G prime, and we run MST on G prime, and like based on the output of G prime, we compute MST on G double prime. So yeah, yeah, so this is one specific algorithm which is called as KMB algorithm in Steiner tree. Okay, we don't have to understand the internal details of the algorithm, but so we have actually parallelized this algorithm something in a novel fashion, I should say. So basically, how do we parallelize such kind of algorithm? We can use wherever there is a SSSP or MST involved, we can use parallel SSSP and parallel MST, right? Yeah, so that is what we did, which is our first version of GPU implementation. But then we did not stop here, because each of the parallel SSSP we have to run k many times, right? So those SSSPs will have to happen one after the other. So each of the k SSSP happens from a different source. It is not from the same source. So yeah, otherwise, like, yeah, we don't have to run k many SSSP res, right? Like, so each of the k SSSPs happens from different source. So we took an approach which is on the right hand side. uh, yeah, so this is like we made uh, this parallel SSSPs run in parallel. So that is what we call it as a GPU VOpt, which is the optimized version of the version 1 implementation. So how did we do it? Like, we used an approach which is called as double barrel approach. So why do we call that a double barrel? So, like, an SSP happens in parallel. So to run two SSSPs, we have to run one after the other. But instead, we can actually use double barrel technique, which is yeah. So uh, which is the following, which this can be generalized to any PSSSPs. Uh, yeah, so how does this double barrel work? So there is this double barrel gun. We load two bullets and press a single trigger, which triggers both bullets, right? Yeah, so this is the inspiration, or this is the crux of our technique. So we are going to load treat the operator formulation, the do while loop, right? So that as a bullet, we are going to load two set of SSSPs into the operator formulation approach, and just run the operator formulation. um, uh, then it will actually compute SSSPs from two different sources. So which will yeah, so what I have been talking will get clear in a few minutes. So yeah. Okay, so this on the left hand side, if we see, so this is so we initialize the distance to some infinity, right? So similarly, we initialize distance of source to 0, right? And basically the do while loop, we call it as fixed point here, and we perform relax till there is no change, right? So double barrel works this way. We just have to double the distance arrays and initialize appropriately and give it to the same kernel. Just that we need to launch it with 2n many threads for the double barrel approach. So yeah, this the changes are highlighted here. We use distance array as 2n, and the source corresponding to source 1 is 0, and n plus source 2 is 0. And basically, with no change or minimal change to the kernel, we can actually use the same kernel and perform two parallel SSPs in parallel. Yeah, so this is what we have achieved. In fact, we have achieved much more than that. We have generalized this to uh, mm, uh, like any p parallel SSPs can be run in parallel. So we have made it as an tunable parameter, such that if you pass like how much parallelism you want, because we don't have enough memory on GPUs, right? So based on that, like, we can actually tune how much parallelism that we wanted. So this approach actually helped us um, improve our performance. So the key takeaway here is, like, push approach and pull approach has their own benefits, which we have seen a little earlier. And so as topology driven and data driven and hybrid approach, each has their own benefits. And yeah, like, similarly, double barrel approach works great with operator formulation approach, and this double barrel approach can be extended to an n barrel approach as well. And the T optimization actually quickens the or speeds up the fixed point iterations, and makes the convergence faster. And similarly, when there is T delta, we can use shared memory, which improves the performance. So overall, combining all the above optimization, we can get a peak performance for any graph algorithm that is being implemented on GPU. So yeah, so these are the techniques that that actually helped us in our research. And yeah, so any questions I can take. So
Thanks, Rajesh. Any questions from anyone? All right. So if there are no further questions, we are going to stop here. Let's thank Rajesh, who gave us this graph-related processing, how to do that efficiently on GPUs. I'm sure some of you who are trying your course projects related to graph algorithms, or even otherwise, you might be able to find some of these aspects quite useful in your course projects. All right. So there are some of the thank yous coming in the chat, Rajesh, for you. All right, so we'll stop here. Thanks a lot, everyone. Thanks, Rajesh, again.
thanks, Rupesh. Thanks for inviting me.